Okay, so back for binomial theorem, Pascal's triangle and Pascal's triangle. So this is going to be a little bit out of order in terms of the textbook because the binomial theorem relates very heavily to Pascal's triangle, as we will see. So if I have x plus y squared, what is the distribution of this guy? It's going to be, it's going to be x squared plus 2xy plus y squared. Or what is this? So that's what this guy is equal to. About x plus y cubed. So then it's going to be x plus y times this thing. So that's going to be x cubed plus 2x squared y plus xy squared plus x squared y plus 2xy squared plus y cubed. And that right there is equal to x cubed plus 3x cubed y plus 3x, sorry, so this should be squared, y squared plus y cubed. And now the last one that I'll actually write out here will be x plus y to the fourth. And that's going to be x to the fourth plus 3x cubed y plus, so then that's 3x squared y squared plus xy cubed plus yx cubed plus ex squared y squared plus 3x y cubed plus y to the fourth. That right there is going to be equal to x to the fourth. And then we have 4 6x squared y squared plus 4 xy cubed plus, cool. And then also x plus y, so the 1 is equal to x plus y, and x plus y to the 0 is equal to just 1. And we can think of these guys as having 1s and x to the 0 here. Y to the 0 also. Cool. So what was the point of all of this? How does this relate to things that we were just covering? Well, it relates to them via the fact that this guy right here is n choose 0, x is 0, y is 0. This guy right here is, sorry, n is this power right here. So this guy right here is, we're asking how many ways there's to pick 1. So it's 1 choose 1 plus 1 choose 1, or is 0, y to the 0, y to the 1. So this is how many 1s, or how many x's there are. Up here, this guy right here is n choose 0, where n is 3. Right, I should use here. So 3 choose 0. This right here is 3 choose 2. This right here is 3 choose. So 3 choose 0. So this is 3 choose 3, which is the same thing as 3 choose 0. What this comes down to is, am I looking at how many x's I'm picking, or am I looking at how many y's I'm picking? So it ends up being symmetric, hence my confusion there. Sorry about that. And 3 choose 0. So that's the coefficients. And if we look here, we get 4 choose 4, 4 choose 3, 4 choose 2, 4 choose 1, and 4 choose 0. And it turns out that that's always going to be the case. That right there is the binomial theorem, that if we have x plus y to the n, that it follows that formula of x plus y to the n is equal to the sum of n choose k of x, y, where this guy is the k, this is n minus k. Cool. And we can sub out these guys. So if I actually had x plus 2z, then I could just plug in 2z for y here, and then it would actually, the coefficient would be 2 to the n minus k times this thing, because my y is 2z. So this is a bit more general than it looks. So now I'm going to jump over to something that looks very different to start, but turns out that it's pretty related. So this right here is something called Pascal's triangle. Blaise Pascal is one of those old polymaths whose name pops up a lot. He invented the syringe. His Pascal's wagers, very famous argument for why you should believe in God in philosophy or religion. It's called the negative argument for the existence of God. He's a mathematician, obviously. He's a general philosopher, wrote Penses. 4, 5, 4, 1. So he's one of those old polymaths who is influential in lots of different fields. And then, so what are the rules here? The rules, we can think of there being a bunch of invisible zeros going out here. And here I'm getting the next level is equal to the sum of the two things that are kind of adjacent above it. So 1, if I'm adding zeros, then these sides are always remain as 1s. Then I sum these two guys up and I get 2. And then I sum these two to get 3, and then the 1s stay on the outside. And then the same thing here. Then 3 plus 1 is 4. 3 plus 3 is 6, not 5. That's what I get for distracting myself. 3 plus 1 is 4, blah, blah, blah. We would keep going. We would get 10, 10, 5, 5, 1, 1, and so on. But this right here turns out to be the same thing as basically just having a bunch of binomial coefficients, or it's related to the binomial coefficient, but it looks identical to the, so right here, this is my first row. This guy's like my 0 row, 0th row. So we have to start counting at 0 for this to be nice. But this guy right here, that is 1, choose 0. This guy right here is 1, choose 1. This guy right here is 2, choose 0. This guy right here is 2, choose 1. This guy right here is 2, sorry, this is 2, choose 2. This guy right here is 2, choose 1. This guy right here is 3, choose 2. And 3, choose 1, and 3, choose 2. And 3, choose 0. 3, choose 3. And so on and so on. So right here, Pascal's triangle, fairly surprisingly, ends up just relating, or being the binomial coefficients. So now, what do we have next? We have, so these going across the row of Pascal's triangle, because these guys are always going to be equal to the coefficients of, or to the binomial, to choose functions, which are also the same thing as the coefficients in the binomial theorem, that we can go across this row, and that will give you the coefficients attached to the binomial theorem. So right here, if I want to do x plus y to the 5th power, then I wouldn't have to actually do it out. I could just say, okay, that means that it's going to correspond to the 5th row of Pascal's triangle. So it's going to be x to the 5th plus 5 x, and then y to the 4th plus 10 x squared y cubed plus 10 x cubed y squared plus 5 x to the 5th y plus y to the 5th, by just going across. So if you just want to do the summing up of Pascal's triangle, then you can get that. And this is a result. The reason that we know that this holds true is because we can do it by induction using n minus 1, k minus 1, plus n minus 1, k is equal to n choose k, which is in your textbook, and this is, you guys do that. Okay, so now this was asked, we were asked to do this during with just the binomial theorem. And with just the binomial theorem, you would want to use this guy to the n, and this would be x minus, so this, the sum of the coefficients here is going to be 0. So when we raise it to the power of n, we should expect that the sum of the powers is still going to be 0. So if we have x is equal to y, then we should know that x x to the n, y to the 0 plus n choose 1, x to the n minus 1 y, all the way over to n minus 1 x y n minus 1 plus n choose n to the y to the n. If we set y equal to x, then x minus y is equal to 0, therefore this thing, therefore x minus y to the n is equal to 0. Therefore, we would have to have n choose 0, x to the n, plus n choose 1, x to the n. Oh, sorry, these guys alternate. So this should be minus. And then this will be plus or minus, and then this will be minus plus, depending on if this is odd or even. So this should be minus. And this is just saying whatever it should be, and then this will be the opposite of that. X to the n is equal to 0, therefore the alternating sum is going to be equal to 0. So therefore this is equal to 0. So because x can be anything, we can set x to 34. And we still have to have that this is equal to 0. Why is this obvious when n is odd? When n is odd, it's even more obvious because, well, let's just show it for the case of 1, n equals 1, and then we'll show it for n equals 3. So then we would have minus this, except these guys are the same because this is 1 choose, so this is n choose k, and then this guy is n choose n minus k, and we have them subtracting. So these guys are clearly going to cancel, and that's pretty easy to see. And when we have n is odd, then we have n choose 0, and then at the end we'll have n choose k, and then we'll have plus n choose 1, and then we can rearrange this so that we have n minus choose n minus 1, blah, blah, blah. And these guys all cancel. When it's even, our work is a little bit more cut out for us because we don't have them pairing off like that. And then you can also prove this using Pascal's triangle. So leave that as a little assignment for you guys of prove this. Using it shouldn't be that hard.